Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So this week will be the last of this three-part mini-series that I'm doing on matrix inversion. And today we're really going to focus on how we can go about conducting some more thorough tests of the code that we looked at in the previous episode. So if you haven't seen those episodes already, there's the previous but one episode we talked about the theory of the technique of Gauss-Jordan elimination and how we can use that to calculate the inverse of a matrix. And then in the previous episode, we looked at how I have gone about implementing code in C++ to actually make that algorithm work. Okay, if you want to see either of those two videos, if you haven't seen them already, I'll put links in the description below, otherwise links up here as well. So go and check those out if you haven't seen them. So the focus of what I want to do today, as I said, is to have a look at how we can do more extensive testing. Now, really, the proper way to test an algorithm like this is to have some kind of ground truth data. So what we need is a set of matrices, and then we need a set of their inverses calculated using some other technique, or in this case, some other software that we know, or at least we believe to be correct. And we put all of that together, and then we call that our ground truth data. And then we take the same matrices, we invert them using the algorithm that we created last week, and then we compare those results to the known ground truth, and if they match to at least within a degree of tolerance, we talked about that last week as well, then we know that our code is working as it should. If they don't match, if there's a big difference, then clearly we know that there's something wrong. So I've approached this by writing code in Python using the Numpy library to compute a set of matrices and their inverses, and then I've outputted all of that out into one .csv file, and then I've created code in C++ to read that CSV file in and convert all of those numbers into the QB matrix class instances that we can then invert, and then we can compare the inverse of those matrices calculated using our algorithm with the inverse of the matrices that we've got from Python and the Numpy library. Now, of course, I'm assuming that I think quite rightly so that the Numpy library is going to calculate these results correctly. I have no reason to think there's anything to question that in any way. So we can safely assume that that is a gold standard or the ground truth to which we can compare the results from our code. The advantage of doing it this way is that we can do really extensive tests. It's no problem to create, for example, a set of 10,000 matrices and their inverses, and then we can run all of those through our code in one go, and we can get a good feel for whether our code is working correctly or not. Okay, so just before we go to the computer and have a look at how to do that, I just want to say, as I always do, that if you like this video, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, let's go to the computer and let's have a look at how we can do more extensive testing of our matrix inversion algorithm. Okay, so here we are at the computer, and what I've got open here, this is the Python code that I've created to allow more extensive testing of our QB matrix 2 class. And as I said in the introduction, really the point of doing this with using Python is firstly so that we can have an easy way to automatically generate a large set of matrices that we can use to test our algorithm. Now, of course, we could do that in C++, but we need some form of gold standard for the inverse to which to compare our algorithm so that we can tell whether our algorithm is working correctly or not. Now, the gold standard that I've chosen to use is the Numpy or Numpy library that's available for Python. And I think it's pretty fair to assume that this is a reliable gold standard. I mean, there's no reason to doubt that. So the basic idea is that we're going to run through and generate a set of random matrices, and we're going to invert them, and then we're going to output all of that data together into one CSV file, and then we're going to write test code in C++ that's going to read that CSV file in, and it's going to generate the QB matrix 2 objects from that data and perform the inverse, and then compare the result of that inverse to the result that was generated from the Python code and stored in the CSV file. Now hopefully that will make sense as we go along. So this is the Python code that I've put together, just called generate test matrices.py. The first thing we do obviously is import the libraries that we need. We import Numpy as NP. That's pretty straightforward. Then going to define the dimensions of the matrices that we're going to create. I've stuck with just doing 5 by 5 matrices. We only need to define the number of rows because of course our matrices have to be square by definition. Only square matrices are invertible, so the number of columns and the number of rows are always going to be the same. We then simply define how many matrices that we want to generate. In this case I've specified 10,000, which I think to be a reasonably good number to conduct a test. And then we're simply going to loop over that, so just have for I in range 0 to num matrices, a very straightforward way of doing a for loop in Python. I know you can do various other ways in perhaps more Pythonic syntax, but anyway, that's how I've gone about doing it. And then for each iteration through there, each time through the loop, we generate the matrix simply using the random.randint function from the Numpy library, so np.random.randint, and we want to generate with a range of values from 0 to 20. Our size is equal to num rows and num cols, and then we subtract 10. So what that will do is give us a range of values in our matrices that vary between -10 and +10. We then compute the inverse of that matrix using the inverse function from the linear algebra library in Numpy, so np.linalg.inv a, and that gives us a_inv. And then we concatenate those together. So the point is as we go along, we want to build up one array that contains all of the data. So if I is less than 1, so if this is the first iteration, then we simply do b equals np.concatenate, and we're going to concatenate a and its inverse together along axes equals 1. Now that will put them together horizontally by column wise, so it will put the inverse of a to the right of matrix A. So we have the original 5 by 5 matrix, and then we have the 5 by 5 inverse of that will go next to it, and that will give us a final matrix of 5 rows and 10 columns. If I is not less than 1, in other words this is not the first time through the loop, then we do a double concatenation. The first part of this is we concatenate A with its inverse as before to give the 5 row by 10 column matrix that we just talked about. But then we want to concatenate that onto what we have already, so we concatenate that onto B along axis equals 0. So that will put the new matrix and its inverse below the matrix and the inverse that we counted previously. So the first time through this B is going to be 5 rows and 10 columns. The second time through this B will be 10 rows and 10 columns. The third time through this B will be 15 rows and 10 columns. The fourth time through it B will be 20 rows and 10 columns, and so on. Once we've finished all of that, we've looped through and we've generated all of our matrices into one array. We simply use np.savetext to write B out to a file, which I'm calling test.csv. We specify the delimiter as a comma, and we want one header line simply to contain the number of rows, in this case, which is 5. So we do header equals string and num rows. And that's everything that we need. When we run this, it will go through and it will generate a file containing 10,000 matrices, which we can then read into our C++ code, and I can just demonstrate that now. If I go to my terminal window, I've already set this up with a virtual environment for the Numpy library. I don't like having everything just installed in my default environment anyway. And then we just simply have to run Python and generate test matrices.py. And if we run that, that will then just run through and that will generate 10,000 integer matrices of dimensions of 5 by 5. Okay, so once that's complete, if we look in that folder, we have here test.csv, which contains the values that we want. If we do more test.csv, we can see that. We see that we have the header, which is hash space 5, and then we have our values 5, -7. It gets a bit unwieldy to read in this format, but anyway, there we go. That's exactly what we want. Now the interesting challenge comes from how do we actually then read that data into C++, and that means we need to implement C++ code that's going to read CSV files. Okay, so I'm going to show how I've approached doing that. So I'm in my file here now, testcode2.cpp. Okay, we bring in a whole bunch of stuff. Mostly this is the same as we had for the test code that we used previously. Obviously we hash include QB matrix, and we need fstream and string stream. Those are two new ones. We then have the print matrix function that I talked about before, so we don't need to cover that again. And then we have our int main. First thing we do is we define the file name of the file containing the ground truth data, just using string from the standard library. Notice I'm using test1.csv here because I know this happens to be a particularly good example. So when I ran the Python code to demonstrate before, I didn't want it to overwrite this one. Anyway, we'll see why in a moment. We then open our file using ifstream, so ifstream input file name. If the file is open, then we do stuff. If it isn't, then obviously something's gone wrong and we don't need to do anything. We then declare a string object called current line, and we use getLine to get the first line from the file given by input into current line. Now this line is in the format of hash space n, where n is the number that we want. So we have to split the string around the position of the space. Okay, so we use size t here to declare a variable called delimiter position, and we're going to use current line.find space. So that will give us a number representing the position of the space in the string, and then we're going to use the substring function from the string class to create a new string. N row string is equal to current line.substring delimiter position current line.length. And what that will do is divide the string that we've got here called current line around the space, and we're only interested in the string from the space and onwards. Okay, once we have that part of the string we're interested in, we then convert that to an integer, and we can use that value then as the number of rows. So we use a to I function to convert that to an integer from the C string object. Okay, we then need to read the rest of the file and pass each line as we go. Now this is slightly different. What we're going to do is define a string stream object called ss, and we define a variable called current number of type double. So we're going to read our numbers in as type double. So current row is going to hold all of the elements that make up the row that we've just read. So we're going to read it line by line. Each line is going to be stored into current row. And then we're going to, as we go, we're going to store the data into a matrix, but this will be a 5-row by 10-column matrix, okay? And what's going to be called current matrix data. And we're going to create a vector of QB matrix 2 pointers so that we can store the matrices that result in any failed tests. So as we're going through this, because we're doing, say, 10,000 or so tests, we want to be able to store the ones that fail. We're assuming that only a very small number might fail, so we want to store those specifically so that we can go back and look at them later and use that as diagnosis, as a part of diagnostic testing if we need to. We then set up the total number of rows, row count, number of successes, and the number of fails as integer variables. And then we simply loop until we reach the end of the file. We use getLine on input to get the current line into current line, and we then convert the current line into the string stream object ss. And then we're going to loop through the string stream and extract the numbers around the commas. And we do that simply this way. It does have a while loop, while ss into current number. And we use current row.pushback current number. And if we peek into ss and see that the current element is a comma, then we ignore that. And that will just loop through, and that will bring out all of the numbers and put them into current row. So at this point here, current row now contains all of the numbers that we've read in for this line. Okay, so that's in this case going to be 10 numbers. We then clear the string stream object because we don't need it anymore. We do that with ss.clear. And we're going to concatenate the contents of current row into current matrix data, which will be one large single dimensional array. Okay, so current matrix data.insert, and we add to that current matrix data.end. Okay, so we want to insert from the end, so from current matrix.end, and we want to go from current row, the current row from beginning to current row.end will be inserted onto that. So what we're doing is we're putting that together. So each time through, each line is 10 elements, 10 numbers long, and each line that we read in is then going to be concatenated to the end of current matrix data. So the first time through, this current matrix data will then contain 10 numbers. The second time through, the next 10 numbers are added to the end of that, so it will then contain 20. And the third time through, it will add the next 10 numbers onto the end of that, so it will contain 30, and so on. We then clear current row, ready for the next loop, and we increment our row count because we've now finished reading this row. Now, the interesting bit, if we have read 5 rows, then we want to stop and form that data into a QB matrix 2 object, because we know that we are making 5 by 5 matrices. Now I have hard-coded this. We could do all this derived from the number in the header, but yeah, well, I haven't done that, so it doesn't matter. Do bear in mind, if you want to work with different size matrices, you will have to, of course, change these values. Okay, so if we've read in, so if row count is greater than 4, so that means that we've now read in 5 rows, okay, we reset the row count back to 0. We create a QB matrix 2 object of type double called new matrix of dimensions 5 by 10, 5 rows by 10 columns, and we put into that current matrix data, all the data from current matrix data that we've been building here as we go along. We then define 2 new matrices, QB matrix 2 objects, both of type double, called left matrix and right matrix, and we're going to use the separate function that we talked about from our matrix class to divide new matrix into the left half and the right half around column number 5. Okay, we talked about the separate function in the previous episode, so if you want to know more, go and have a look at that. There will be a link in the description below. Now the right-hand side now contains the ground truth inverse loaded from the CSV file, whilst the left-hand side is the original matrix that we want to do the inverse. Okay, so we want to invert the left-hand side ourselves and then compare the result with the right-hand side. So we call the inverse function on the left matrix, and then we're going to use the compare function with a tolerance of 1 times 10 to the minus 9 to compare left matrix with right matrix. Now remember, right matrix contains the gold standard ground truth inverse that we've read from the CSV file. Left matrix now contains the inverse that we have calculated ourselves, and we use the left matrix dot compare function there to compare left matrix with right matrix. We do that to a tolerance of 1 times 10 to the minus 9. Because we're using double precisions, it doesn't make a whole lot of point to test for absolute equality. It's not always going to be achieved. Okay, so we specify a tolerance. If that is successful, then obviously we display invert test succeeded and we increment the number of successes. Otherwise we display invert test failed and we increment the number of failures. And in the event of a failure, we push the matrix back into our failed tests array of QB matrix 2 pointers so that we can refer to those later if we want to. Okay, coming out of that, we then clear current matrix data, and then we increment the total number of rows, and we simply go back to the beginning. And that will loop through, and that will read all of the data in. We don't actually store the data. The only matrices we store are the ones in the failed tests. All that we're actually doing is counting how many successes and failures we get. And we come to the end, and then we print out any matrices that cause the tests to fail. But to do that, we just loop over every matrix that we have a pointer to within our failed tests array or vector, okay, using that syntax, and then we just print those out. So that's really very straightforward. And of course we display the number of successes and the number of failures, and then finally close the file and return 0. So that's all of the code. Now if I go to my other terminal window, which is here, now we're going to run that. We can compile it very easily, g++ -o testcode2 testcode2.cpp minus std equals c++17. Okay, we'll just compile that. Right, and then we simply run testcode2, and that's going to read in all 10,000 of our matrices and perform the test. You see, it's immensely fast, even with my screen capture software running. Now the interesting thing is here, we see we've had 9,999 of these succeeded and 1 failed. Okay, so what we have here, this is actually the matrix read in from the CSV file with the ground truth inverse. So this is the first row to here, and so this is the original row of the matrix, and then this is the calculated inverse. Now this is actually the result from our gold standard ground truth, and these numbers we can see immediately are highly dubious. It seems pretty unlikely that we would in reality get numbers like that. So this makes a very interesting case to have a look at in more detail. So if I simply go into Python and I want to import Numpy as np, so that we can use that. And what I'm going to do, let's just move that down to here so I can see. I'm going to create an array like this containing these numbers. So this contains -6, -2, -2, 5, 5, like that. And I need another square bracket there, like so. And then that's the first row. The second row is 4, -1, 2, -5, -2. And then the third row is -4, 0, 4, minus 5, 4. The third row is minus 4, 9, 4, minus 2, 5. And then the third row is 1, 3, minus 2, 4, 0. Okay, and if we display that, we can check that that is indeed right. This is where this gets a little bit interesting. If we do b is equal to np.linalg.inverse of a, like that, and if we do print b, we see that we get these numbers of order times 10 to the 14 and times 10 to the 15. So we get these very, very large numbers, which are, you know, almost certainly not really correct. Now, the interesting thing is to think about why is this happening? And in fact, the reason happens is because this particular matrix is very close to being singular, which means that calculating its inverse becomes, as a matrix approaches being singular, then calculating the inverse becomes less and less meaningful until eventually you get to a singular matrix, whereupon calculating the inverse is in fact entirely impossible. So obviously in this case we must be getting close to that. How can we prove that? Well, we can prove that by looking at the matrix determinant. So if we print out the determinant np.linalg.determinant of a, we see that we have a number 2.13 times 10 to the minus 13. So the determinant of the matrix that we were trying to invert is very close to 0. Now, it is the case that for a matrix whose determinant is 0, it is impossible to calculate the inverse. As the determinant becomes very close to 0, then the result that we get from the inverse becomes increasingly unstable. And so for a matrix like this, which has a determinant of something times 10 to the minus 13, then actually it doesn't make any sense to calculate the inverse of that. So that is hugely reassuring, because it means that the fact that our algorithm, our C++ algorithm, failed on that one particular test is not actually because there's something wrong with our code. It's because actually calculating the inverse of that matrix doesn't really make any sense in the first place, which I think is pretty interesting. Okay, let's just quit that, go back to our normal terminal. Now, the other thing that I did, so that was generate test matrices py. I also did this for a floating point version, which is pretty straightforward to do. So this is the floating point version, simply replaced rand_int with uniform between minus 10 and 10, the same size, and we write that out to a file called testfp.csv. Again, we generate 10,000 of those. I don't need to show that. And to use that, we just go back to here and we just modify our file name. So we're going to have std string file name equals .. python code /testfp.csv, like that. Go back to our terminal window here, clear that, recompile our test code, and rerun test code 2. And we see again, we get this situation of 9,999 tests succeeded or 1 failed. Yeah, so this is the original matrix, but we see here these numbers actually here do make sense. So what has happened is simply our result isn't quite close enough to that, to within the tolerance that we specified. And in fact, I remember from when I looked at this before, if we modify the tolerance down to 1 times 10 to the minus 6 and run that again, then everything succeeds. So there's simply a slightly different numerical difference there, and that is going to be the case because probably the algorithm that I've implemented is going to be different to the one implemented in Numpy. There are actually many ways that we could go about implementing the matrix inverse. Doing it using Gauss-Jordan elimination is not the only way of doing it, and the way I've approached implementing Gauss-Jordan elimination is also not the only actual way of doing it. So that's what we get. Now, the interesting thing is, let's have a look at, because we only print out the failed matrix there, and I think it would be quite interesting to have a look at what the inverse of that would be. So if let's modify our test code to allow us to do that. So we're going to print out current matrix, and then I want to separate that, QB matrix 2 double left, well, let's call it something else, original matrix, and QB matrix 2 double original result. Oh, let's call it gold standard, like that. Okay, and then what we're going to do is current matrix separate and into original matrix, and reference to gold standard around column 5, and then I want to do original matrix dot inverse, and we want to print that out. Print matrix original matrix. Okay, hopefully that will work. So let's go back to our terminal. Let's recompile. Original matrix. Yep, because I spelt it wrong. This is why I try not to do things live anymore. I used to do a lot of videos with coding like this, but I've kind of stopped doing it recently, so hopefully that will work. So we'll compile that. Very good. And if we run test code 2 now, okay, so we get down to here, and so what we see, this is the result that we get, and if we compare this, we see that there's minus 0.062 there, we have minus 0.062, 0.006, 0.0. So we see that within the accuracy that we're displaying here, this is correct. They are indeed the same. So the difference is just a small numerical error that occurs likely, in all likelihood, because we've implemented different algorithm to that used by Numpy library. So it's very interesting to think about why it might be that different algorithms are giving different results, and I believe that it is most likely to be because of the limits of the precision of the machine and the environment that we're using to do the calculations. So even though we're using double precision floating points in the C++ code that I've implemented here, they still have a limited precision. They're still 64-bit numbers, but there's still a limit to the precision that they can encode, and therefore rounding errors are going to accumulate as the algorithm goes on, particularly in algorithms such as Gauss-Jordan elimination. As it goes through the various steps, the small rounding errors will propagate through and will potentially become larger and larger. Although they should generally still stay reasonably small. I dare say that even if I were to modify my Gauss-Jordan elimination implementation slightly so that it proceeded in a different order, I would expect that we would get very slightly different results numerically for the same input matrix, for exactly the same reason. Simply doing things in a different order would mean that the rounding errors will accumulate in a different way and in different places in the matrix, and therefore will lead to a very slight numerical differences in the results. So clearly using different algorithms to calculate the inversion is going to give very slightly different results numerically for exactly the same reasons. Now for some reason this particular matrix here, which I'm going to put a copy of in the description below in the CSV format, so you can copy and paste it into other software, whatever you want to use, and you can have a look at inverting this matrix yourself if you wish to do that. It seems to be a bit of an interesting case because it yields numerical differences that are larger than we might otherwise expect. And clearly the other 9,999 matrices that I tested here, they all passed my test, so they were the same between the two algorithms, between my algorithm and Numpy's implementation, to within 1 times 10 to the minus 9. And it's interesting that it is just this one that isn't. Curiously, actually, it is the same to within 1 times 10 to the minus 8. I know I only showed changing the threshold to 1 times 10 to the minus 6, but if you drop it down to 1 times 10 to the minus 8, then all 10,000 of these tests do indeed pass. So it is my firm belief that the differences really are just due to rounding errors. And indeed, I tested the same matrix in a third software package that I used to calculate the inverse, and that produced a third different result that didn't match with either the results from Numpy or from my algorithm. So 3 different algorithms, presumably, for calculating the matrix inverse, all gave 3 very slightly different results. But this is, as I say, to be expected because simply of the limits of the precision of the machine that we're working with. Anyway, there we go. So that is how I have approached testing my code for calculating the inverse of a matrix using the Gauss-Jordan elimination method. And we've also seen how it will appear to fail in certain cases, and compared to our gold standard, and we've seen that that can be due to numerical differences just because we've implemented a slightly different algorithm. But we can also see that in situations where the inverse of the matrix, or calculating the inverse of the matrix, doesn't really make any sense, for example when the determinant is approaching 0, then obviously we're going to get different results, and that does appear to give a test result that indicates a failure. So that really leads quite nicely onto what I want to do for the next video, because the obvious question is, if there are certain matrices that doesn't make any sense to invert, why don't we just test for that first before we actually embark on doing the Gauss-Jordan elimination procedure? And that would, of course, make a lot of sense. And to do that, what we need to be able to do is to calculate the determinant of a matrix, and that's what I want to move on to look at in the next video. Okay, so there we go. That's really everything that I wanted to cover in this episode, and that's going to be the end of our little mini-series on calculating the matrix inverse. There is one other well-known method for calculating the matrix inverse using the determinant and so on, and the adjoints actually, but I'm not going to look at that for the time being. The technique that we have works for at least everything that I want to do, so we're going to stick with that. We have seen that we do have problems if we have a matrix, or we try to invert a matrix that is close to being singular. And it's obviously a little bit inefficient to try to invert that, and it would be very practical if there was some way that we could test whether a matrix is close to being singular or not before we run the inverse procedure. And we've seen that in conditions where that is the case, where the algorithm fails, if we look at the value of the determinant of that matrix, we can see that the determinant is either 0 or at least very close to 0. So clearly, if we had a way of calculating the determinant of the matrix, then we would have a simple test that we could perform before going about trying to calculate the inverse that would tell us whether or not the inverse computation was likely to be successful. So in the video next week, what I really want to focus on is how implementing the code required to calculate the matrix determinant, which I hope will be of interest. Anyway, I really hope you've enjoyed this video. It's been a great deal of pleasure making it, and if you have liked it, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Okay, well listen, it's been a pleasure. I hope you've enjoyed it, and I really look forward to seeing you in next week's video. Thank you very much for watching. Bye.